Yeah, we looked at equivariant convolutions on Riemannian spaces, and today we will see how this can be generalized to arbitrary manifolds. And if you have a topologically non-trivial manifold, then this means that you can't have a global coordinate chart or not a global trivialization of your tangent bundle. And this means that we have to ensure that whatever we are doing is independent from the choice of coordinates. And this is why we call this coordinate independent CNNs. But if manifolds have symmetries, isometries for Riemannian manifolds, then we still want that our neural networks are equivariant with respect to these symmetry groups. So I guess there couldn't be a better proponent of coordinate independence or the principle of covariance than Albert Einstein. And when he was developing his general theory of relativity, he formulated this principle, which states that the universal laws of nature are to be expressed by equations which hold good for all systems of coordinates. So if you have some situation which you want to describe that's actually coordinate free, physics doesn't know anything about coordinates, and then you can choose different coordinate systems to describe the same thing, and it looks different numerically. You have different tensor coefficients or so, but these different coefficients encode exactly the same thing. And of course, this shouldn't only hold for the laws of nature, but also for deep learning. And yeah, you saw this slide already a lot. We are also looking at active transformations of our signal and want to be equivariant. And I want to compare these two things to each other. So what we did until now was only looking at active transformations. Here on the top, where you have your signal, and then you really actively rotate or translate your signal. But instead, you can also look at passive transformations, which do not change the signal itself, but they kind of change the coordinate system which you put on the signal. And these two viewpoints are dual. So if you have an active transformation, you can also view it as having a passive transformation of your coordinate system. And from the observer who sits in the coordinate system, these two things look exactly similar. And if you have active transformations, you get equivariant neural networks. If you have passive transformations, you get coordinate-independent neural networks. But these things are not necessarily the same. So you could also describe a non-equivariant network in a coordinate-independent manner. But the point I want to make is that if you have a weight-sharing process, let's say of a kernel between different points, or if you don't know in which coordinate system you should apply your kernel, if you don't have a preferred coordinate system, then you actually need equivariance. So equivariance and weight sharing together implies, coordinate independence and weight sharing together implies equivariance. And if we're on manifolds, we will mostly not look at such charts, but instead we will look at local reference frames and then gauge transformations between local reference frames. So I will talk in the second part about these neural networks on manifolds, but this gauge principle is a bit more general, and first I want to motivate that in this more general setting. So what is a gauge theory? A gauge theory is always then used when you have some physical system or data which you want to describe, but there's no single canonical mathematical description of it. And yeah, so an example would be if you have a Euclidean space without the coordinates chosen. So we are not looking at a Euclidean vector space RD, but just a plain Euclidean space without coordinates. Then it's not clear which coordinate system to choose. And you have to choose some coordinates arbitrarily. And yeah, this is what I call here in a more general setting, a gauge has to be chosen arbitrarily. Gauge theories kind of ensure that this redundant degree of freedom doesn't matter in the end. So another example is if we have a set doesn't have an order. But if we implement sets in a computer, then we implement it as a tuple, and we arbitrarily introduce an order. And that's a completely arbitrary choice. So we need to ensure that whatever the neural network is doing is independent from that ordering of these set elements. Or in physics, if you have a potential, then usually the physical dynamics only depends on the relative potential or on derivatives of the potential. So you can sum an offset potential to it. And this is also a very simple choice of gauge. Yeah, and then another example would be if you have graphs, so then you want to represent the nodes somehow on your computer, so you put them into a vector to have a node list, and you get an adjacency matrix. But again, we have to somehow artificially order or label these nodes, and again, we need to ensure that whatever we are doing is independent from this choice. Okay, maybe a very simple everyday example is the weight, gauging of a weighing scale. So the issue here is that we have a physical mass, but physical mass doesn't come with it doesn't have numbers attached to it a priori. So you know that 4 strawberries are 4 times as heavy as a single strawberry, but you can't represent that numerically yet. And if you want to do that, you have to choose a gauge, and we usually do that by measuring this weight relative to a reference weight. So for instance, you could choose 1 kilogram as a reference, and what you're doing is abstractly taking this positive, this line with an end here at 0, and you map it to the positive real numbers if you do this choice. So you assign to each physical weight, like 1 strawberry, you assign a certain numerical weight, which is a positive number, and you can think about it as introducing coordinates or adding axis ticks to this real line or to the weight scale. But of course, you could also have chosen a different reference weight. So here we have also a pound, and then you get different axis ticks. And then these two things are completely equivalent, and we can transform back and forth between them. So we can always have a unit conversions from kilograms to pounds. And this unit conversion in this example here is just a multiplication with a positive real number. So if you look at the set of all reference weights relative to which you are measuring your physical weight, then these gauge transformations will just scale up and down this axis. And you get a gauge group. So these scalings form a group, which are the positive real numbers together with multiplication. But we have to be a bit more cautious. So I said that all different gauges are equally valid, but often we have a certain structure given on whatever we are trying to gauge. And this reduces the set of admissible gauges to a specific subset, which is somehow structurally preferred. And this in turn determines the gauge group. So here in this case, if we are measuring our weight relative to some fixed reference weight, these gauge maps here become kind of linear maps. So we have axis ticks which are equidistant. But of course, we could also have chosen a gauge where we just have any diffeomorphism, and then we get these non-constant axis ticks. And then as a consequence, we get a different gauge group. So transforming back and forth would now be multiplication with a positive number, but it would be any diffeomorphism. And this is important to understand, that the structure on your manifold, this tells you which gauges are preferred, and then you also get the reduced gauge group. So this is the example of Euclidean affine spaces, which relates to the steerable CNNs, which we saw yesterday. And instead of modeling images on Euclidean vector spaces, RD, which come with a choice of origin and a choice of coordinate system, we're here looking at this E2 is just a plain Euclidean affine space, which knows about parallelity of lines, but it probably doesn't have a metric, and it doesn't have any coordinate system or origin given. And the gauges are in this case just coordinate charts, and we can choose global coordinate charts here, which are just maps from this Euclidean affine space to, in this case, R2. And you map over a signal from here to here, and this, otherwise you could think about it as pulling back the coordinate system here to your Euclidean space. And then we could use a different gauge or coordinate chart, XB, and we get a chart transition map. So this map, which maps between these two coordinate representations, is just XA inverse, and then we go along XB to go from one to the other one. And as I said already, we can have additional geometric structure on our affine space, which reduces the gauge group. So in general, these are affine spaces. And if you don't have any additional structure, you have an affine group transforming between them. So the most general affine group where you have the general linear group here as G. But you could imagine to have, for instance, a metric given on your Euclidean space. And of course, you have a metric given here on your Euclidean vector spaces as well. And then you can demand that your chart is isometric, right? If you have metric structure given, then you want that your chart respects that. Both charts would then be isometries, and also your chart transition map is an isometry. So instead of having the general affine group down there, you would have the Euclidean group, which is the group of isometries of the Euclidean space. And then if in addition, let's say you have some preferred up and down direction, like if you would process an image and the images are all natural images upright with some gravity direction, then you could demand that your charts respect that, and then the only ambiguity which you have left are translations. But now it's encoded in this gauge group. And yeah, I think the important difference is that as computer scientists, we always get our images already on a pixel grid. So we always get it in the chart, and then we assume all structure which is given on, in this case, R2 as like inherent to the signal, right? But really, we want to operate on this coordinate-free thing, and then we should always think like, okay, which structure is actually in our problem? Do we have an up-down direction or not? Since if we have a microscopy image, then it comes with an up-down direction, but probably the orientation doesn't matter, so we shouldn't assume that structure. And it's kind of backwards to first assume it and model everything on R2, and then kind of account for this ambiguity of rotation by using equivariant networks. And it's more clean to not assume this structure from the beginning. And this is the viewpoint which we are taking today. So as a third example, we could look at multisets, and they don't have a canonical order. But if you want to implement a set in your computer, you have to do it as a tuple. You have to pick some arbitrary choice of gauge. And then again, you could choose different ordering, and our transition maps would now be permutations. And yeah, what you can also see here in this example, it's a bit more simple to see, that your multiset can actually be thought of as the set of all tuples, and then with an equivalence relation taken with respect to this permutation action. So actually this coordinate-free set is something like an S3 orbit of ordered tuples, and this is how it relates to equivariance. All right, so we saw how to gauge data, but of course we want to operate on data, so we need to look at some layer, which yeah, for convolution networks maps from some input feature map to an output feature map. And as I said, we want to do this in a coordinate-free setting. But then we can go and we can express it relative to gauges. So we choose a pixel grid, and we do it on our input image and on our output feature map. And yeah, then we get this map LA here, which maps between these coordinate representations. And LA is basically defined as XA inverse, then going along L and then back up via X. So if you have this coordinate-free representation of your layer, then from that you can, if you have a chart given, you get the coordinate representation of the layer by pre and post composing it with a chart. And we can do this again with another gauge. So we have a coordinate representation LB of our coordinate-free layer L. And we have our chart transition maps between XA and XB, both in the input and output. And yeah, you get this commutative diagram, which you will see more often in this talk, and it's all over my paper. Since yeah, I always try to express everything in a coordinate-free setting, but then we have to look, okay, how is it expressed in coordinates, and how do different coordinate representations relate to each other? And physicists usually just look at these coordinate representations and forget about the coordinate-free thing, but it's implied, and I think it's quite important to know that this coordinate-free representation is there. And if you look now at this outer square, so we just ignore what's going on in the inside, we see that this looks almost like an equivariance constraint, right? You have a group action on the left and the right, these chart transition maps, and then on the top and the bottom you have a function, but it's not really an equivariance constraint, since equivariance of a function means that you would have the same function at the top and the bottom. And here we have two different functions. So before we always had some function, let's just call it f, and down here also f, and f should commute with these transition functions. But here we have LA and LB, and we don't have an actual constraint on these layers LA and LB, but we just know how they relate in different coordinate systems to each other. So this is the point I wanted to make in the beginning, that coordinate independence is actually not implying equivariance. But if you think about it now, that you have some layer given, some let's say convolution layer, and you want to apply it to an image, and you don't know which coordinate system was chosen, then you don't know, you don't know relative to which coordinate system you should apply your layer. So you have this layer template L tilde, and you don't know whether you should apply it here and in chart A, or whether you should apply it in chart B. So if you want to apply this given layer in a coordinate independent way, you have to apply it at the same time in all layers. Otherwise you make some arbitrary choice here. So we have to set all these coordinate expressions equal to this thing which you want to apply, L tilde, and then you see that L tilde actually has to satisfy an equivariance constraint. So this is a different way of how to arrive at equivariance from this coordinate independence viewpoint. And if we're going to manifolds, then we won't look at global coordinate charts, or also not local, but extended coordinate charts, but at such choices of local reference frames at each point. And gauge transformations will then be local transformations between these points here, between these frames at each point. And yeah, in physics, they often call these local reference frames observers, and I think that's a quite nice intuition of some observer, which I visualize here as a satellite, which is flying over Earth and looks from different direction on your signal. And yeah, if you are such an observer, you don't know how you are rotated relative to your signal. And of course, in our application, this observer will be the kernel. Our kernel observes the signal, but it could observe it in different rotations, and we somehow have to account for these choices of rotations. And yeah, you can probably already guess that we will account for that ambiguity of rotation by using G-steerable kernels. Other questions so far? Okay, then I will just go on. So yeah, now we will go to manifolds. And maybe I first want to give a motivation of why we are interested in defining convolutions on manifolds. Yeah, I am personally interested since it's a nice mathematical setting, but from the application side, you could do something like segmenting meshes in computer graphics. Then people applied these neural networks to do shape correspondence tasks. You could also try to predict deformations of manifold, since the shape of your manifold, like how this hand is formed, depends on the metric field, and the metric field is a tensor field. So it's in particular a feature field which we could predict. We could predict deformations of our metric field. Then another nice application is this artery wall stress estimation, which was implemented by Pim and collaborators. And I guess you will talk more about it later. Then probably in general relativity, you could apply these neural networks at some point. But of course, we are also interested in Euclidean CNNs, or CNNs on homogeneous spaces like the sphere. And these are in particular also Riemannian manifolds. So we want that our theory on general Riemannian manifolds should, in these special cases, recover what we did before. And indeed, we will see that we will get steerable CNNs on homogeneous spaces, or Euclidean spaces out as a special case in the end. And another point I want to mention before we start into the actual talk is that these constructions are all intrinsic to the manifold geometry. So for instance, if you have this sphere, then you may be thinking about it as being embedded in R3, and you could do some convolution in R3 in this embedding space, but we are not doing that. We are always convolving, or whatever we are doing is in the surface of that sphere. and this is what it means to be intrinsic. Okay, so some questions which arise if you want to design a convolutional network on a manifold. The first one is how to define your feature spaces or feature fields on the manifold, and we do it in a very similar way. So we have fields of different geometric types rho. So you could have a scalar field, vector field, a tensor field, and it's just prescribed by some group representation rho. Then we need to think about the convolution kernels. And the problem here is that the geometry of the manifold may look different at every point. So it's hard to share a kernel between different points. But what people are usually doing is to define the convolution kernels on the tangent spaces. And all the tangent spaces are isomorphic. So at least we can put a kernel down on the tangent space. And then we map it down via the exponential map. So we place it on the tangent space and then we project it down. Then the next question, which is actually the most tricky one, is how to share weights over the manifold. So you have a given kernel and you want to apply it at every single position. And there's some ambiguity in it, and this is actually what will lead us to gauge equivariance. And finally, we have to think about isometry equivariance. So if you have this egg, then you have this rotation around the z-axis as isometry group, and or it's a subgroup actually, and you want that rotations of your signal on this egg commute with the convolution operation. Okay, so we can brainstorm a little bit to get a feeling about what is the problem with sharing weights between different points. One approach which you could take coming from homogeneous spaces is that you could try to share weights by demanding equivariance with respect to a global symmetry group. For instance, on the Euclidean space, we had translations, or we had the affine group, or if you are on SO3, you can share weights by demanding SO3 equivariance. And in these cases where we have a homogeneous space, we can, this group action moves every point to every other point, and this will enforce a global weight sharing between all points. But if you are on a non-homogeneous manifold like this egg, you will only get weight sharing on your orbits. For instance, on the egg, you have rings around the egg. Or if you have a completely asymmetric manifold like this monkey head, then you don't get any weight sharing. So this principle somehow doesn't work for us. Then another approach which many people take is they think about sharing weights on Euclidean space as taking your kernel and shifting it around, which you can formalize as a parallel transport. And this is indeed path independent on Euclidean space, so you can shift along different paths and you get the same kernel always. But if we are going on a curved space or non-orientable space, then suddenly parallel transport becomes path dependent. So if you shift, you define your kernel somewhere and you shift it up along this path or along the other path, you see that the rotation of your kernel changes. So this is a consequence of the curvature of your manifold. Or another example is the Mobius strip, which is actually a locally flat manifold. So you won't get rotations, but since you have this twist in the Mobius strip, if you go once around it, you will end up with a reflected kernel. So again, we have an ambiguity, and somehow we need to resolve it or deal with it. And indeed, it turns out that this choice of rotation or reflection of a kernel on a manifold is actually inherently ambiguous. And that relates to topological obstructions, but I guess you will understand that later. And people propose some solutions. The first one is that you use gauge invariant features. So for instance, if you on the sphere, you don't know in which rotation you should apply your kernel, then you can just use a rotation invariant kernel, problem solved. This is not really expressive, since this kernel cannot encode any rotational information. You can kind of only map between scalar fields, but you cannot produce something like a vector field which encodes a direction of features. And this example here is where people start to apply one non-symmetric kernel in different rotations, and then they pooled over these rotations, and again you get an invariant response. And this is actually corresponding to a regular representation. So what they would do is do a convolution which lifts from a scalar field to a regular feature field, but then pull it back down to a scalar field. Then a second approach is to choose a gauge or reference frame or kernel alignment in a heuristic way. So for instance, you could do a parallel transport, and there are indeed papers who say, okay, we define our kernel at some arbitrary point on the manifold, and then we transport it to all other points along the shortest geodesic. But yeah, that sounds a bit arbitrary. And if you would deform your manifold a bit, then also your geodesics change, and they can even change in a discontinuous way. So yeah, I think you can define it, of course. And actually, our theory in the end will also cover such solutions as special cases. But it's somewhat arbitrary. Yeah, the second example there is if you have an embedded manifold, then people use the embedding curvature. So for a surface, you have two principal curvature directions and or two curvature directions, or the curvature is kind of a matrix. And you can diagonalize it, and then you go into the direction of the in the more curved direction you align your kernel. But that's actually also somewhat arbitrary, since if you deform your manifold, that might also flip around. And on a manifold like a sphere, this is not even well defined. And even on a cylinder where it is well defined, you have two directions of your principal curvature. So again, some ambiguity. But maybe for some manifolds, this is actually a reasonable choice. So for instance, if you have a sphere, then you could use such a, this spherical coordinate system, which is at least up to a certain extent regular. And you could make a point that it's useful to use this coordinate system to align your kernels. Then the third approach which people looked at are spectral approaches. So you can actually define a Laplace-Beltrami operator on your manifold, and then you get eigenfunctions. And you could define a convolution in the spectral sense as taking your signal and multiplying the spectral components. And this is gauge independent, since this whole spectral construction is coordinate free by design. But the spectrum is unstable under deformations. So here you see some spectrum plotted, and this guy is kneeling down, and then this function is changing completely. So this also doesn't really generalize well over different manifolds. So it's again not useful. And then our solution is to not use gauge invariant features, but gauge equivariant features. And this actually contains the invariant features as a special case, and it also contains this here as a special case. And just choosing a certain kernel orientation, a fixed one, would then correspond to choosing a frame field on your manifold. And then, well, I will explain it later. I think it will become more clear then. Yeah? Yeah. Yes.
Related in principle, but quite different setups. So one of them uses explicitly the vectors of the plus and like the Fourier transform released for some of the early works, for example, like Mobius. So this is indeed stable, as you show in this image. But other methods like the Chebyshev method, or that was used on graphs and serial approaches that were used in meshes since probably the mid-90s. First one, like the album. So these are actually stable. Yeah, I'm saying that the spectral methods, so it refers to two approaches that are related but different. So one of them uses explicitly the eigenvectors of the Laplace as an analogy of the transform on the topological basis. The space of functions are made over the graph, and this is unstable. So spectral filters like polynomial filters, like what was done by the Pescara. So you can actually filter these are stable, the deformations of the. So what you show here is the first.
Okay. Yeah.
Also gauging, right? So they're isotropic, their rotation is symmetric.
Okay. Maybe you can point me to some literature, since I would be really interested in that. Yeah. And what I should maybe also mention when we are talking about spectral approaches is there's not only the Laplace-Beltrami operator on the manifold itself, but you can also define a Laplace operator apparently on the frame bundle. This would also probably be a bit more powerful and correspond to our gauge equivariant features. But I didn't look into that in detail. Okay, so we had an ambiguity of the choice of kernel rotation or reflection or kernel alignment in general. And we somehow need to formalize that mathematically to deal with it. And we do an identification here of a choice of kernel alignment with a choice of local reference frame at that point. So having this frame or another frame means that these two frames are rotated relative to each other, so they correspond to rotated kernels. We kind of take our kernel and project it relative to the reference frame. And this implies that if you have a frame field given on your manifold and you have a kernel, then this induces a kernel field on your manifold. And this canonical frame field, if you have R2 as a very special case of your manifold, actually corresponds to this kernel field, which you use in a standard convolutional network. But you could also look at an alternative frame field and it gives you an alternative kernel field. And that thing is probably not particularly useful, but our theory can still describe it. And since we now identified the ambiguity of the kernel alignments with the ambiguity in the choice of reference frames, we have to look into how far is the choice of reference frames ambiguous. And this is formalized by something called a G-structure. Yeah.
Are you restricting just to parallelizable manifolds? I mean, you are assuming that your manifold is in some sense globally a global frame.
So locally, we will trivialize our manifold. Yeah. So locally, we will choose a gauge and apply our kernel in a certain orientation. But if the bundle is non-trivial, then you can't do that indeed. And this relates to G-structures. So G is the set of gauge transformations which you have between frames at each point. And if you have a globally parallelizable manifold, then this is actually a trivial group structure. Yeah. So the frame bundle you can think of as the set of all reference frames of all tangent spaces. So at each point you have a tangent space, and you can choose all different reference frames of a tangent space. And if you attach that at each point to the manifold, you get the frame bundle, as you see here pictorially. And these frames at one point have GL valued transition functions, right? Since if you have if you have two different frames, they relate by some matrix multiplication, some change of basis, and you can use any invertible matrix as a change of basis. And the group of all invertible matrices is the general linear group. So the transition functions are general linear. And the G-structure is simply a sub-bundle of the frame bundle with transition functions which are in some subgroup G. So for instance, this image here doesn't actually show all reference frames at one point, but you see that these reference frames are only related by rotations. So this should actually be an SO2 structure on the manifold, what you're seeing here. And for the mathematicians here, we have the G-structure is a principal bundle or bundle, and we can locally trivialize it. So if we look at the local neighborhood U around some point, we have pi inverse U. This is the bundle over this local neighborhood U, which we cut out. And then we have a local trivialization or gauge A or gauge B, and it kind of maps our it maps this to the base space U times our fiber. And if you have a G structure, the fiber is simply the group G itself. So think about it in the case of an SO2 structure here. You have all rotated frames, and they look like a circle, right? Topologically. Or in other words, they look like the group SO2, which means you kind of stick something like SO2 to each point. And this is why we have U times G here in our local trivialization. And you can choose different gauges, so different identifications of this part of the bundle which we want to trivialize with U times G. These are different gauges, psi A and psi B. And then we get here gauge transformations between these these two trivializations or transition maps, and they are an identity on U, and on the second part it's just a multiplication with the structure group element, which is just an element of G. So in the case of this example here with SO2, you would just have a rotation of your frames, which relates two frames into each other. Yes.
Last question is that a single group element, or is it like a group element assigned to each one U?
Yeah, very good point. Yeah, it's a group element assigned to each point. Yeah. So it's kind of like if you have an overlap, yeah, actually this U is a shorthand for, you have UA for trivialization A, you have UB for trivialization B, and then you have the intersection, and this is what I just call U here. And on this intersection, you have at each point, you have a group element which transforms your frames into each other. And yeah, here I have some bit more visualizations of what it means to have a G structure. So for instance, here, if you have the trivial group, you have only one frame at each point, since your gauge transformations are trivial, right? You have only one frame. And you could have a different frame field. So having a G structure just means that the transition maps between frames at one point are G valued, but it doesn't tell you which, for instance, frame field you have. Then if we have the reflection group, this means that at each point on the manifold, we have two reflected choices of frames which you could take. And again, we can have different reflection group structures. Then here we have an SO2 structure on the Euclidean space, or some scaling structure. And then, yeah, this trivial group structure up here corresponds to polar coordinates. And you see that you get a singularity in your origin if you make that choice. So it actually doesn't live on the Euclidean space, but on the Euclidean space with the origin taken out. You have a singularity there. Yeah, and then again, you could add reflected frames also. Here you see an SO2 structure on the sphere. And next to it, you see a trivial group structure on the sphere. And there you already see a problem. You have singularities at the poles. And that relates actually to the Harry-Ball theorem, which tells you that you cannot comp a coconut, as Chris said. Yeah, more mathematically expressed, you cannot find a continuous vector field. And in particular, you can also not find a continuous frame field on a sphere. That just doesn't exist topologically. So if you want to reduce your G structure or structure group from SO2 further down on the sphere, that doesn't work. You will always get some singularity, or you will always get some discontinuity somewhere. It just doesn't work. And yeah, that has important consequences for designing neural networks, since if you want to build a network which is transforming your feature fields in a continuous or smooth way, then to describe that, you need a continuous or smooth G structure. And you cannot go further down than having a SO2 structure. So that's actually strictly necessary to look at such non-trivial G structures, and therefore also at the G-steerable kernels on topologically non-trivial manifolds. And since it is a topological property, that also applies to this monkey head, which is topologically also just a sphere. And then another example is the Mobius strip, and there we have a different topological obstruction, which is that it is a non-orientable manifold, since you have this twist in it, which means that you have to have these reflections in your transition map somewhere. So you have a reflection group structure at least, if you want continuity. So I didn't finish my slides on Monday on fiber bundles, and I just have 2-3 slides which I put in here to make that maybe a little bit more formal. So if we look at the tangent bundle, that is formed by the tangent spaces of a smooth manifold. And we have a total space given as the disjoint union of all tangent spaces. Just think about taking together all tangent spaces, you get your tangent bundle. The fiber is RD. So since the tangent spaces are vector spaces, that is modeled by a Euclidean vector space. You have a projection map which sends points in the tangent bundle to the manifold in the obvious way, such that if you have a vector at TPM, it's being mapped to P in the manifold. And now we can look at local trivializations. So if we take a subset UA of the manifold, we can trivialize the bundle over UA. And since our fiber is RD, we map it to UA times RD. So locally, it looks like a trivial bundle or product. And you see that if you map these tangent spaces to R2, you kind of assign coordinates to them. So you can think of that as inducing you a gauge or a choice of reference frame on your sphere. And again, you can choose a different trivialization at another point, and then you have that UA and UB overlap somewhere. And you get transition maps between these two trivializations. And yeah, we have this psi B or psi A inverse composed with psi B. And this gives you an identity on the base space. But in the fibers, we have this structure group GBA acting. And as Pim pointed out, you have a different group element at each point. Since you have many tangent spaces here in this overlap, and at each point, you will get some gauge transformation. And so how does that relate to G-structures? So first of all, these local trivializations identify our tangent spaces in a linear way with our fibers RD. Since these are vector spaces, you want to preserve that structure, and then you demand that your trivialization is linear. And then your structure group elements will be general linear group elements, if you make that assumption. And how do you get from a general linear group to some structure group G, which is a subgroup? You assume some additional structure on your manifold, and therefore on your atlas of trivializations. And so, for instance, if you have only the smooth structure, your fiber trivializations are at each point just linear maps, and you get all reference frames, and you get GL as transformations between them. But let's say on the sphere, we can choose an orientation. And we can say, okay, we only look at left-handed frames. Then our fiber trivializations are orientation-preserving maps. And our structure group elements would be GL+. So we don't have all matrices with the determinant non-equal to 0, but all the matrices with determinant larger than 0. Then if you have a volume form given on your manifold, you can say, okay, I want that my gauge map preserves the volume of tangent spaces, and you get unit volume frames. And as a gauge group, you get the special linear group, which has determinant 1. Then if you have a Riemannian metric given, you have, you can restrict here to isometric maps, and you will get orthonormal frames everywhere. And your structure group would be OD. And actually, if you're talking about the metric structure, that is one-to-one equivalent to a choice of G structure, where G is the orthonormal group. So a Riemannian metric is exactly equivalent to a choice of OD structure on your manifold. And actually, that's a very nice way of unifying all these different structures. Like, okay, you have a volume form, you have an orientation, you have a metric. That sounds very unrelated. But actually, from this G structure viewpoint, it's very similar. It just gives you a different structure group G and a different set of trivializations of your bundle. And it's kind of unified here. And this is what we are taking to design our neural networks. And if we have G as a structure group, then we get G-steerable kernels. So we know how to deal with it. And as a last example, which you were pointing to already, if our structure we could call the global trivialization of our manifold. Then our identification here is a unique map. We get a global frame field on the manifold, and we have a trivial structure group. And we have topological obstructions. I said that already. If you have, for instance, a non-orientable manifold like the Klein bottle, then you cannot reduce your structure group in a continuous way beyond having reflections in it. Okay, so back to my actual talk. So we have our Riemannian manifold now, and we have a G structure on it. And what that implies is that you cannot distinguish or you cannot prefer reference frames further than up to G value transformations. So if you have a just, let's say, generic Riemannian manifold, you have an OD structure. So the metric tells you, okay, you can restrict to off-normal frames, but you don't know which rotation to pick or which reflection to pick. You have this ambiguity inherent in your problem. And this implies that any object we are expressing on the manifold or any morphism between objects has to be expressible relative to any frame from this G structure at that point where the object is living. So as an example, we can look at tangent vectors in the tangent space, TPM, and these vectors are completely coordinate free. They don't know anything about reference frames. But if we want to implement it, we need to choose the reference frame. So yeah, and this here is now a local trivialization, but looked at only at one point P to make it a bit more simple. Yeah, and this gauge map is kind of mapping TPM to R2, as you saw it before. And on the one hand, this gives you coordinates. So it maps V to some coefficient vector VA, which here would be just coefficients 1, 1. And at the same time, it gives you a coordinate system or reference frame on your tangent space. Then we could have chosen another reference frame the whole time, and you would get yeah, a different frame or different coefficients, square root 2, 0 if you rotate by 45 degrees, for example. And then we have gauge transformations, GP. So this is now really only at one point P, and if I drop this P, it's really this whole field of gauge transformations. And this BA means we go from gauge A to gauge B. And this changes your coefficients. And the important point is we have different numerical coefficients, so it kind of looks different for the computer, but geometrically it encodes the same object relative to a different frame. And yeah, what is maybe a bit more interesting for us in our application are feature vectors. And they should also be expressible relative to any frame of the G structure. And if we have a feature vector field of type rho, this is what you saw already, then we define it here as, well, if you have the coordinate expression of it in gauge A or gauge B, you get a c-dimensional trivialized feature vector out. And these coordinate expressions relate by FB is equal to rho of GBA FA. So you know that if you, let's say, rotate or reflect your reference frame, you know how your feature vectors will transform. And this is exactly the same as you saw yesterday already. But yesterday we looked at active transformations of our signal, and now we look at passive transformations of our reference frames. But except from that, it's exactly the same thing, just a different interpretation. And yeah, as said yesterday already, if we have a trivial representation, we get the scalar field. If we have the standard or defining representation of G, we get a tangent vector field. We get tensor fields, irrep fields, regular feature fields. Whatever representation you come up with gives you some choice of feature field. And since there are mathematicians here, I also want to show this a bit more formally. So you actually call that a G-associated feature vector bundle, which this is more or less what you saw before, only that now our fibers are c-dimensional feature vector spaces. And you have different gauges, and then these fibers transform according to rho of GBA. And what it means to be G-associated is that if you have two different bundles, so here we have the trivializations of our G structure and the trivialization of our feature vector bundle, and that they are associated means that if you change the trivialization in one of the bundles, you also change it in the other bundle. So they kind of transform in a synchronous way. So here you would have a change of reference frame by GBA, and your feature trivializations will transform by rho of GBA. And this is maybe, if you're a physicist, you know that from tensors, if you have like a tensor expression changing, or let's say you have a vector field, then it changes by yeah, some group element G. Your covector field transforms according to G adjoint, and the tensor field according to tensor products of that. But they all transform kind of in the same way with their own representation rho of G. And we will have something in our neural networks where in each layer we have a different feature field. And then if we change our frames, all these feature fields are G associated to our G structure. So all their coefficients will change by their particular rho of G. Is this clear, or do you have questions regarding this construction? All right, then Yeah, what I also still want to say about feature vectors is that a feature vector field would formally be something which you call a bundle section, but it's just a choice of feature vector at each point in the manifold. So intuitively, it's, I think, very clear what it means to have a feature field. Okay, so we looked at objects on the manifold, but we also need to look at morphisms between objects. And as a very simple example, we can just look at a linear map on the tangent spaces. And such linear maps are a priori coordinate-free objects. So we just have here TPM, and we map with M from TPM to TPM and do something like projecting this vector. As you saw before already, you can choose gauge A, and then this linear map relative to gauge A is just a matrix, MA. Relative to gauge B, you get a matrix MB. And you have these gauge transformations on the left and right. And this tells you that the coefficients of your matrix MA and of your matrix MB relate by left and right multiplying with G and G inverse. And this is how you know how matrices transform. Okay, so we are not really interested in something like linear maps on our tangent spaces, but we want to design a convolution which is GM coordinate independent, which is why we call it a GM convolution. And we have certain requirements on this convolution. So first of all, we want to map a row in field to a field of type row out, as before. Then what makes it a convolution is that we want to share a given kernel between all points on the manifold, as you can see in the picture. And then finally, of course, it should be GM coordinate independent. So we have these three requirements. And as I try to argue here, this will require that the kernel which you share needs to be G-steerable. Otherwise, you can't satisfy this, this GM coordinate independence and weight sharing at the same time. Okay, so we have to think about what the kernel is on a manifold. And we saw before in steerable CNNs that in coordinates, the convolution kernel is just a map from RD to matrices which are C out times C in dimensional. And we will use exactly the same construction here. But now we need to lift that on a manifold somehow. And yeah, this kind of suggests, since we identify RD with our tangent space at point P, that our kernel at P is a map from TPM to this thing here, HOM from A in P, A out P, and these are our feature bundles. So A stands for associated, since these are associated feature vector bundles. And this space HOM A in P, comma A out P is the space of linear maps from input feature vectors at P in a coordinate-free setting now to output feature vectors at P in a coordinate-free setting. And if we would put that back into coordinates and trivialize it, we would just get C out times C in matrices. So we just identified this RD and RC out times C in with the actual geometric objects on our manifold. And this is a kernel at one point, but we can globally define a whole kernel field on the manifold. And yeah, this is then motivated by this here, a map from TM to this HOM A in A out, which is actually a bundle with fibers, which are these linear maps between the input feature space at that point and the output feature space at that point. And these linear maps again form a linear map bundle or homomorphism bundle. But actually these linear maps again just form a vector space, so it's again just a vector bundle. So it looks abstract, but it's just taking these kernels. So we had kernels in coordinates, then kernels in a coordinate-free setting at one point, and now we have them as a bundle on the whole manifold. And if we would just have this upper part here mapping from TM to this HOM bundle, then we could map in such a way that, so if we wouldn't have these projections going down to M here, we could map in such a way that we are at P in the manifold and we have a tangent vector at P, but we map it to a homomorphism at another point Q. We don't want that. We want that our homomorphism also lives at P. And we do that by requiring that this thing here commutes. So they should, after projecting, we should land in the same point on the base space. But if that's too abstract, just think about having coordinate-free kernels instead of our coordinate expressions at every point. So I just wanted to mention that for completeness. Yeah, and this is a general kernel field in a coordinate-free setting. But if we want to have a convolution, we need to look at a very specific type of kernel fields, which are so-called convolutional kernel fields, which share kernels between different points. Okay, now again, we can express everything in coordinates. So what you are seeing here in the middle is now again a kernel just at a point P, which is mapped from TPM to these homomorphisms of the input feature space at that point and the output feature vector space at that point. And then here on the left, you have the trivialization of TPM in gauge A with RD or in gauge B with RD. And you have the gauge transformation GBA in between. So this is what you saw before. And then on the right, we have this homomorphism bundle. And yeah, you can define, actually these trivializations are induced by trivializations of your input and output feature vector bundle. And this homomorphism bundle is again something associated. But anyways, you just map these linear maps here of feature vectors if you trivialize it to C out times C in matrices. And what we are interested in is how does this thing here transform? And if you do the mathematics, you would have to read it in the paper, but you get out that the gauge transformations are basically row in adjoint tensor row out, and then you also have this volume scaling factor popping up there. And again, we can now just look at the coordinate expressions and forget about the coordinate-free thing. And what this tells us is that they relate in this way here. And yeah, this looks very suspicious already, again, like a G-steerability constraint. But it's, again, actually not, since we have the coordinate expression Ka and Kb in our commutative diagram. So this is not the same map, but two different functions. And we just, yeah, this here just tells us how a kernel in gauge A and a kernel relative to reference frame B relates to each other, how to translate between them. But we can still have a completely non-equivariant or non-steerable kernel and express it in different coordinate systems. So yeah, it doesn't require G-steerability yet. But now again, think about it. If you have a given kernel and you want to place it on your manifold, you don't know relative to which frame you should place this kernel. So if you want to stay coordinate independent, you have to ensure that it shouldn't matter relative to which frame you share it. So the only choice you can make here is to share it relative to all the reference frames at the same time. So this is what is there. We say that the coordinate expression in gauge X equals to our shared kernel K. And oh yeah, I should have put K here in this commutative diagram, since our coordinate expressions Ka and Kb become equal to this shared kernel K. And then we get this equivariance diagram. And yeah, you get this constraint down here, and it's just our G-steerability constraint written down in a slightly different way than yesterday, but it's exactly the same. So that is maybe the most important takeaway, that if you want to apply a convolution on a manifold and you have this G structure on it, which means that you have a G ambiguity of reference frames at each point, then you need a G-steerable kernel. So again, as a bit more concrete example, if you have a sphere, for instance, you don't know how to rotate your kernel. How do you resolve it? You take a SO2 steerable kernel at each point. And then if you would rotate your kernel on the sphere, the feature vector which you get out at that point would just somehow transform according to some SO2 representation. This is the whole idea. So fancy algebraic setup, but intuitively it's very simple what is going on. Yes?
In that notation, that is rho in minus t, does that mean inverse and transpose?
Inverse and transpose, yes. Yeah, yeah. It's the adjoint representation. Yeah. And yeah, you get that since here you have matrices, and you have G acting from the left, sorry, row of G out acting from the left, and from the right you have row in inverse acting. But if you kind of vectorize this matrix by stacking like the columns into one vector, then you get this tensor or Kronecker product, and then you need to add the transposition to it. Yeah. Okay, so with that we can summarize what the GM convolution is. So what do we have given? We have a Riemannian manifold M. Then on top we have a G structure given. And that maybe already sounds weird to you as a mathematician, since if we have a Riemannian manifold, we have a metric structure on our manifold, which is an OD structure. So we already have a G structure, but we can choose an independent G structure, which either adds more information and then it needs to be compatible. So let's say we are on a sphere and our Riemannian metric gives us an OD structure. But then in addition, the G structure could say, okay, we are only interested in left-handed right-handed frames, and then you would actually get an SO2 structure on the sphere instead of an O2 structure. So it can add more information, but it can also, we use it here also to have more flexibility in our design choices of the neural network. So if we want to have something like scale equivariance, we can also add, even though we have this Riemannian metric, we can add frames of different scales, and then we get scale equivariance. Okay, so we have a Riemannian manifold, and we have a G structure on the manifold. Then I didn't talk about it yet, but we also need to parallel transport feature vectors to accumulate them from different points, right? The kernel looks at a whole patch of the feature field, and then it accumulates it. We do that via parallel transport. And this parallel transport has to be G compatible. What that means is if you have a Riemannian manifold, you have your Levi-Civita connection given on it. And if you are just assuming a G structure, which is compatible with your metric structure, then that's fine, you can use it. And this is what many people do, but let's say you choose a frame field which is not closed under the parallel transport. Then that is not able to describe that connection or parallel transport, yeah. And then you need to, this actually enforces you a different connection on your manifold. And we need to go to that very abstract setting, since people are actually building such neural networks which are not compatible with the Levi-Civita transport on the manifold. So maybe that becomes more clear if I draw a picture. So the simplest setting is just if you have something like R2 and you have reference frames, a frame field which looks like this, or a standard frame field, and then transporting around a frame from here to another point would just mean we get this frame here, right? Simple, nothing happens. But if our frame field, if we choose a weird frame field here, which kind of starts rotating these frames, then it's impossible to transport frames according to the Levi-Civita connection, since this frame here doesn't live in our G structure, which we are assuming, right? So having this choice of frame field here would actually forbid us to use the Levi-Civita connection. And why do we look at that? Since if you're on a manifold, then people use these heuristics to choose frame fields on the manifold, like based on the curvature or something like that. And then, well, they don't think much about parallel transport and just take feature vectors from everywhere and copy the coefficients over, which amounts to a transport relative to such a trivial E structure. So then, the transport is just copying over vectors, and to accommodate these applications in our abstract theory, we need to look at these G-compatible connections. Since, Levi-Civita connections only make sense if you have a G structure which is an SOD structure or an OD structure, and then if we assume more structure, throw away certain frames, we can't look at general Levi-Civita connections, but we have to look at something more general. And then finally we need a G-steerable convolution kernel on our manifold. And having that, we can apply our convolution by, we do two steps. So the first one is we apply what I call a parallel transporter pullback of the feature field to the tangent spaces. Since I said we take our kernel and we put it on the tangent space and project it down, but actually we do the opposite. We have it in our tangent space, and then we have a pullback of the feature field back to the tangent space. And it's not just a mere pullback, since the feature vectors at different points live in different feature vector spaces. So we also somehow need to have an isomorphism which brings it into the feature vector space at the point where the kernel is living. And we do that by additionally parallel transporting it along this geodesic. So this transporter pullback is taking feature vectors from an area around your point where you want to apply your kernel, transporting it, so then everything lives in the feature vector space at the point P, and it's attaching it to a point V, which corresponds to this point XPV, where we took the feature vector from. And this is intuitively how a local observer at the point P would see the feature vector field. And yeah, after this transporter pullback, we match this kernel in the tangent space with our, so yeah, the pullback field is matched with the kernel, which is just this integral, but it's like a standard convolution then. Or like the convolution at one point, just multiplying the kernel with the feature vector field. And we get an output feature vector at that point. And yeah, since our kernel is G-steerable, this guarantees that the choice of rotation or alignment of our kernel is completely arbitrary. Okay, so now we define convolutions, but I also promised you to look at isometry equivariance. And for that, we look at something a little bit more general, which I call a kernel field transform. And it's just like a convolution, applying a kernel everywhere, but it assumes a general kernel field, so it does not assume weight sharing for now, since we want to see whether we can derive weight sharing from equivariance principles. And yeah, we have this theorem which looks at some subgroup of the isometry group, which I call I. And then we have this isometry equivariant kernel field transform corresponding one-to-one to an isometry invariant kernel field. And this is what I told you on Monday already, that equivariant maps are always themselves, they have some invariance in their neural connectivity. And yeah, for instance, if you have that example here and you want to be equivariant with respect to rotations of that egg, then your kernel field needs to be rotation invariant, which means that you have weight sharing along the orbits, but not between orbits. And actually your isometry group also includes reflections of the egg. And then in addition, you have this stabilizer subgroup at each point, which are reflections. And actually from that viewpoint, you will also end up at reflection steerable kernels, but with a different derivation, and you don't get global weight sharing. But well, yeah, we still have that, that weight sharing over orbits. And from the theory perspective, it's important to see that a kernel field transform is equivariant if the kernel field is invariant. And with that, we can now look back at convolutions. And since they are defined relative to some G structure, we need to look at this very specific isometry subgroup, which I call Isom-GM, which is that subgroup of isometries, which are at the same time symmetries of the G structure. So that's probably more clear if I show these two examples. If we have this frame field here, then the isometry group of that thing is just translations of the frame field in horizontal direction, but no vertical translations or anything else. And if we have that reflection group structure here, we have both horizontal and vertical translations as isometries, but also horizontal reflections, which preserve that thing. Why did we look at it? Since if we have a G-steerable kernel, we share it relative to some frame here in this G structure, right? And then we get these frame fields here out. And yeah, the important thing to note is that this kernel field by construction inherits this symmetry. So if you have Isom-GM as symmetry of your G structure, you get Isom-GM as your symmetry of the kernel field, which you are applying. And then with this previous theorem, which said that an isometry invariant kernel field transform corresponds to an isometry invariant kernel field, we see that actually these convolutions are equivariant with respect to the symmetries of the G structure. And that is very cool, since we can now just design G structures and then somehow design in symmetries in the G structure, and we know, okay, what is our equivariance of our neural network? Yes?
So the question is that how exactly do you define isometries here? Is it matched with the ring automorphisms, right?
Exactly, yeah. Yeah, and yeah, so we look at the isometry group of the manifold, not of the G structure itself, but we look at those isometries which are still symmetries of the G structure, in the sense that so if you have an isometry or some diffeomorphism or anything like that on your manifold, it induces a push forward on your tangent vector bundles, right? And if you have a push forward on your tangent bundle, since your frame bundle is, or your frames are a collection of tangent vector, it also induces you a push forward on your frame bundle and on your G structure. And the symmetries of the G structure I'm talking about here are push forwards of this isometry group on the G structure.
So just to understand, maybe I'm not seeing the difference. So these are intrinsic symmetries, right? So or are you talking about the possibility of deforming the manifold? So I feel like a map between two different things.
No. If I write isom M, this is the isometry group of the manifold M. So you look at automorphisms or maps, diffeomorphisms from M to M, which preserve the metric.
So the generators of this group are given.
Yes, yeah. Even though we don't look at these infinitesimal things, but yeah. Okay, so now we can look back at our G structures, which we had here, and reason about the equivariance of the GM convolutions relative to these G structures. So the first one, the top left, is our standard trivial group structure, and it's invariant under translations, so it corresponds to a translation equivariant standard CNN, which is the thing you all know in a more abstract language. Then the second frame field up there is, well, it doesn't have any symmetries, so you wouldn't get any isometry equivariance. Then for this reflection group structure here, the symmetries are translations and reflections, so you get a steerable CNN, which is translation and reflection equivariant. Here for that one, again, you don't have an isometry or symmetry of the G structure, so you don't have global symmetries, but at least locally your reflection equivariant. Then here you would get an, the symmetries are SE2, so translations and rotations. Here you have translations and scaling. Then up there, actually someone proposed that model in polar coordinates, and what you get there is rotation equivariance, but only around your center, and you lose translation equivariance. But you could do it in principle, and then the next one on the top right, they would have rotation equivariance around your center, but also reflection equivariance of your model. Then this SO2 structure on the sphere would give you SO3 equivariance, since any rotation preserves that thing. If you have the other SO2 structure on the, well, it's a sphere without the poles, so topologically it's a cylinder, but you get rotations around your z-axis as equivariance group. Then if you have something like this monkey head, you don't have any isometries of the manifold, so you can't demand isometry equivariance. And on the Mobius strip, you would have reflections of the strip and shifts along the strip. Okay, with that, I will come to some applications. And how much time do I still have? Should I go quickly? 6 minutes, okay. Yeah, then I will very quickly. Yeah, I will very quickly go over it. So, yeah, what we're doing here is basically just cutting the strip open in our implementation. And then here you have these parts which are glued together in a reflected way. And yeah, we just implement a convolution on that thing as like within this strip, it's just a trivial convolution with a steerable kernel, so a reflection steerable kernel. And then the parallel transport over this cut edge is non-trivial. And we do it by taking features from one end, putting it to the other end, reflecting it, and also G-steering it with a reflection, and also to the other side, and then we just run a convolution, and that's a simple toy model of our GM convolution on Mobius strip. And yeah, of course, use Mobius MNIST to test what is going on. Simplest thing you can do. And we compare it with the standard CNN, which doesn't know anything about, so it knows about the topology, we copy stuff over, but we don't have steering, it doesn't have any steerable kernels, and it performs worse. And in particular, it's not isometry equivariant, while our models are all isometry equivariant. And yeah, then we test different field types, and regular works best, as always. And the sign flip representation somehow does not work very well, so it over-constrains the problem in some sense. It's just an empirical observation. We also implemented that in an earlier paper on the icosahedron as an approximation of the of spherical CNNs. And we do that by taking this icosahedron and we cut it open at the north and south pole along all these colored edges here. Then you see you get this angle defect, so the parallel transport over these cut open and spread out edges will be non-trivial, and within it will be trivial. We choose a certain gauge, and then yeah, we kind of shear that thing down to a standard pixel grid, which also shears the kernel. But then, having done that, we can just run a standard convolution within each patch, and to implement the parallel transport, we copy and steer stuff over along these edges, which belong to each other. And it actually works quite well, better than the spherical CNNs of other people. And Pim actually generalized that to an icosphere, which takes that grid and projects it back up to a real sphere. Yeah, and then we also have an implementation on the mesh together with Pim, or on general meshes, but he will talk about that. And in our paper, we have like something like 70 pages of literature review, where we show that all this theory actually describes lots of models. Like all these citations, every citation is a single paper, which proposes their own way of doing things on different spaces, like Euclidean spaces. Then you have these, we call it punctured Euclidean space, where you have these weird spherical G-structures. Then we have spherical CNNs and mesh CNNs, our Mobius CNN, and all these models are described in our theory. So it's really unification of everything. And yeah, we choose different manifolds. We have different structure groups, different global isometry groups, different field types or group representations. But if you make the correct choice of all these, yeah, these parameters, hyperparameters, you probably call it, then you can recover all these models, which is quite interesting, and it shows the power of differential geometry. And then finally, I want to give you a short overview over the paper. Yeah, I guess it's probably a bit scary since it's very long, but actually you don't have to read the whole paper. So we have this first part here, which explains everything in a very intuitive and pictorial way. With these point-wise gauges, so you don't have to look at what a mathematician would care about, but you completely get the idea if you read here chapter 3, which tells you how, yeah, what feature fields are, and chapter 4, which designs then the convolutions. So this is kind of what I talked about today. And then we have our implementation, and then here we have a more theoretical part, and we have our literature review, and then yeah, some appendix with all kinds of mathematics and proofs and stuff. And to wrap things up, yeah, yesterday we looked at active transformations of our signals on Euclidean spaces and demanded equivariance. Then in the beginning this morning, we saw that, okay, we can also view that from the passive viewpoint, which is actually necessary to generalize everything to manifolds, where we look at local gauge transformations. But if we have symmetries on our manifolds, we get active isometry equivariance back. So that kind of closes the circle. Yeah.
Okay, thank you very much. It's beautiful. Questions or remarks?
Yeah.
I have one question about the early slide.
Which slide?
Yeah, it's one where you decide that the kernel can be equal for each choice of A and B.
Yeah. Yeah. I will first get this slide.
The one, the previous one.
Oh, the previous one.
Okay.
I think you were talking about this here with Ka and Kb, no?
Yeah, it's the previous.
Oh, the previous one. Yeah.
So we say that we want to design a convolution operation which is parameterized with this spatially shared kernel.
Right, yeah.
Then we say that we allow, potentially it could be different for each point in the manifold, because it's written in the law, right?
Yes, okay. Yeah, yeah.
And then we conclude that it has to be the same on any point. So
Right, yeah.
is this because it's an implication of the second of the slide after of the reasoning we make with the computation map, or is it like what's the point?
Yeah, so the question is, I said if we want to have a convolution, we want to have spatially shared kernels. But down here I write that a kernel field has potentially different kernels at each point. And yeah, so if we look at the general kernel field, I first define mathematically what a kernel field is. And a kernel field could have different kernels everywhere. But then a convolutional kernel field is a kernel field with shared weights.
Then in the slide after, you said that all the kernels need to be the same, kpx equal k. So is that an implication of this slide in the computation method?
So that we share between different points, P and Q on the manifold, is just something we demand. So there are different ways of defining a convolution. So you could go along the spectral way, or yeah, spatially. Usually, a convolution is something which applies the same kernel at every point, and this is something we demand. And here, that Ka and Kb at P are equal. Here is also the P missing. This comes from the gauge transformations at P. Yeah, but this spatial sharing is something we didn't derive, and actually you can derive weight sharing along isometry orbits from isometries. If you want to have a sharing along all points, you would have to demand something like diffeomorphism equivariance, I guess, and then you would get global sharing. But the spatial weight sharing we don't derive, we just demand it. Yeah.
Yeah, I have one question. Maybe following this up, does it make sense to actually expect the convolution on non-homogeneous manifold to behave like a homogeneous? Like, why would the kernel need to be the same at every point if there is a way of distinguishing points on non-homogeneous spaces? Yeah.
So the question is why we demand weight sharing on non-homogeneous spaces, since the geometry is different at every point. And indeed, yeah, that's a very valid question. It's just an inductive bias which we are using. But it's like, let's say in a graph neural network, if you look at your graph neighborhood at different points, it's usually not isomorphic. And then as Pim derived in this natural graph network paper, you don't get weight sharing between these points necessarily.
Right.
And yeah.
Maybe a second question, which might be naive because I don't have familiarity with the meshes and stuff, but in general, like, it's very hard to know the current mass for the exponential map when it's a mess. Like, as soon as you go beyond sphere and Mobius strips, like, so this sphere is, you know, it's very nice, it's how you do gauge stuff, but like, how do you actually access this type of information? Because you assume, I think, both to know the graph structure beforehand and to have access to current transform exponential map. So I'm going to talk about that. Okay. I'm going to talk about the answer later.
Yeah, I will just very shortly say something about how to implement an exponential map or logarithmic map on a mesh. And the exponential map is actually quite easy to implement. You just have a length, you have a direction, you start walking in this direction on the mesh, and you walk over faces until you hit an edge, and then at the edge you just move over to the next face and go in the corresponding direction. And there's code for that. I think we used. Yeah, well, you will talk about it. Yeah.
Okay. Now.
Other questions? I have one.
Yeah.
Or a philosophical question, probably. So, when we are building such an architecture, we are in some sense using a domain knowledge, a priori knowledge of the problem. This problem is G equivariant, G invariant, so I will build such an architecture. And then that architecture will be trained, will work very, very well. But if I show a child this bottle, what is this? It is a bottle. What is this? It is a battle. I mean, they are learning this kind of rotation invariant. The fact that the problem they are looking at is rotational invariant, but they don't, I assume they don't know it in advance.
Yes, I think it is a property which is learned.
Yes.
Yeah. So
the question probably is there a way to learn that a problem is G invariant?
Okay, so the question is, what we are doing is we always assume some symmetry group on our space or manifold and enforce equivariance. But yeah, if you have just a child or an animal, it learns equivariance apparently. And whether there's a way to learn it here. And yeah, of course, you can just throw an MLP on it and hope that it learns it, but it's less parameter efficient.
Yes.
Yeah, in the limit of infinite data, it would probably work better.
Yes.
But it's just an inductive bias which improves performance empirically. But
so it's probably still related to the problem that maybe neural networks are not yet really imitating what's happening in our brain.
Yeah, I guess probably you just have a much more data which you see as a child, and then you have enough to learn everything. There's an interesting experiment where they take cats and put them into an environment which has only horizontal stripes, or into another environment, another cat which only sees vertical stripes, and they really don't learn to see the other stripes. So if you take the horizontal stripe environment cat and put it then into a neutral environment and put a chair in it, it cannot see the things of the stair and walks against it. It just cannot see it, but it can jump on the chair since the surface where you're sitting is horizontal. And if you take the vertical cat, it doesn't walk against it, but it cannot jump on the thing since it cannot see the horizontal line. So I guess
this is a real experiment.
There are some cruel experiments, yeah. But it is, yeah. So it seems to be learned, I guess, implied from that experiment.
Okay, thank you. So coffee time. Thanks again.
Thanks.